Okay then, I think it's time to start now. Yeah. Hi everyone, I'm Ufuk. I'm a committer at the Flink project, and I work at a Berlin-based startup called Data Artisans, where we are devoted to developing Flink in the open. Data Artisans actually came out of the initial contributors to the project, and today I want to introduce Flink to you. Maybe just by show of hands, who has already used Flink here today? Okay, good. I hope I'll get the others excited about it today, so you can also check it out. I will be talking about unifying stream and batch processing, and what I mean by this I'll explain in a few minutes. So looking at Flink, what is it? In a nutshell, it's a distributed stream processor, and it has a unique set of features that I'm also going to explain today. So if you want to summarize it, it's event time handling, state and fault tolerance, and its performance aspects of low latency processing with high throughputs. But we'll get to that in a minute. Flink is developed as part of the Apache Software Foundation, as many other projects in this area. Think of Apache Hadoop, Apache Spark, etc. And looking at the history of Flink, Flink entered the Apache Software Foundation roughly around 2 years ago, then graduated to become a top-level project within the year. And just last month, we released a version 1.0, which was a very big milestone for the project with many happy users. And in this time, the stack of Flink, this is what you see here, has evolved quite a bit. So to summarize, the main two parts of it are the data stream API for stream processing and the data set API for batch processing. And you see both here. And both of them are compiled down to the same runtime, which is agnostic of the API it's running on. So both your stream programs as well as your batch programs will be actually run as streams. So everything in Flink is done on streams. And this is quite interesting because for the streaming part of things, it gives you low latency, but also you can play some optimizations on the batch side. For example, pipelining shuffles between your maps and your reduces. So the stack is very interesting, and actually I think each part of it can fill its own talk. But what I will be focusing on today is the data stream API, and I'm trying to convince you that some of your batch use cases might actually better fit the stream API. So I want to motivate this at the example of counting. Counting is a seemingly very simple application, but it's extremely widespread. So you have it essentially everywhere. You can think about counting visitors in your logs or counting your ad impressions, whatever. So it's a very general problem. And if you can solve this, this will get you quite far already. So looking at this from the batch side of things, you usually do this by gathering all your inputs. You pick your favorite stream processor, be it Hadoop, Spark, or Flink, implement the job, run it, and then you get all of your output. So this sounds very simple, and with the tools it also gets very simple. But when you start, so for example, here's a program written in Flink's dataset API. So we have a data set of the events. We read them from a file, partition the data by some attribute, in this case the color, then we do the counting. This is very simple and nice, but if you start doing this in the real world, you notice that this concept of all input is not really working because input is produced continuously. So you end up with a more complex architecture where you have to continuously create files which you want to process, and this is a continuous process where you deploy the job not once but over and over again. And this can be made to work, but I think that it's sometimes very fragile because of three main reasons. So first of all, it has many moving parts. So the data is produced here, for example, in your logs. Then you have to gather this data, load it into some kind of storage, for example, using Flume, load it into HDFS. Then you continue to schedule this with a job scheduler like Uzi to run your job. And then, of course, there is the batch processor itself. And all of these tools come with their own learning curves and set of bugs, etc., which makes it sometimes very fragile to get this running correctly. Another thing is that since this is a batch processor, you gather all your input, do the processing, produce all your output. The latency is quite high from the data being produced to where you want to have it, for example, here in the serving layer. So the latency is usually in the range of hours or days. Another problem here is that the way we treat time, in this case, the hourly files here, are not explicit in your program, but it happens with the tooling around your program. So you have this multiple times, and looking at the program again, the only place where you see the time aspect of things is actually by looking at the file you're going to read. And I think that this can be problematic. And having my streaming glasses on, this really looks like actually a streaming use case. As I've said, the data is produced continuously, files are essentially finite streams, and the batch job is also executed over and over again. So of course, this bears the question, why aren't we doing this with the stream processor? So in my opinion, the main problem was before that stream processors were not as mature as their batch counterparts. And this led to a variety of things. For example, custom in-house solutions which were not available for the general public in the form of open source. Or the batch processors were abused, as we've seen before, with all the tooling around it. Or Lambda architectures were deployed, where because the stream processors of the time could not handle, for example, the throughput that you needed for the streams, or they could not give strong consistency guarantees. And I'll get into this, what I mean by this, in a minute. So now, actually, I don't think that this is the case anymore. We have a new generation of stream processors like Flink, which are very well suited for the job. And if we can really go all the way, streaming all the way, this will also simplify this architecture. So we replace here the storage and scheduling essentially by a message queue. You can think about Apache Kafka, which is responsible to store the streams in a durable way and provide some kind of replayability. And then, of course, the stream processor, which is responsible to do the actual processing on your streams. And in my opinion, Flink is a very good fit for this use case. And I want to exemplify what makes it special and what are the features you should be looking out for when picking any kind of stream processor, actually. So the three main features are, in my opinion, explicit handling of time, state and fault tolerance, and the performance you get with this. So starting with the treatment of time, what we saw before in the batch architecture, we aggregated all our events in these files, for example, per hour. This doesn't really work with streams because they are potentially infinite. So we need to do this aggregation inside of the stream processor. So, and this is where windows or windowing comes into play with most stream processors. So we group the stream into finite buckets, and then we do the aggregations in these buckets. And these windows can be either time-driven, if you want to have elements in the last X minutes, or data-driven, if you want to say, give me the elements, the last X elements. To make this more concrete with an example, one kind of windows are the tumbling windows, where you don't have overlap between the windows. So essentially what we were doing before with the hourly files, you group the events in these groups, for example, the last 5 minutes or the last 100 elements, and then you do your aggregations on this one. This is nice, but here it takes the window size until you can do the aggregations, until you have the aggregations. So another kind of windows are sliding windows, where you essentially do the same thing. You have a window about a period of time, for example, but you slide this each minute or update this each minute. So with this, you have your aggregations, but you get the results faster because you do this every minute. And these types of windows are actually the simplest kinds of windows you can have. And it's already very hard to do this in a batch architecture. And if you go even further, so if you have proper support for this in-the-stream processor, this gets actually quite trivial. So what we're doing here, this is a data stream program. We consume data from Kafka, partition the data again here with the key by, and then we just specify the window we want to have. In this case, a tumbling window of 1 hour. And now the good thing is that this is explicit in your program, and if you want to change it, you don't have to change the way all the tools interact within your setup, but you can just change one line of code, essentially. As I've said, the kind of windows we saw were actually very simple kind of windows. You can go even further with this and do this more dynamically. So with, for example, session windows, where you define the window actually on certain elements. In this case, by looking at the activity of the event. So if you have a gap here that is longer than X minutes, for example, we say the window ends, and we group this as one window, which we call a session. This is also very nicely possible in Flink. So essentially the same program, but we just change within this program one line of code and say we want session windows with a gap of 10 minutes in between sessions. So if you have a gap of 10 minutes, this defines a new session. And thinking about time, actually, you have to differentiate between different notions of time. So there's, on one side, you have the time when the event happened. This is often part of the records you are consuming. For example, if this is a tweet, this would be the time when the tweet happened. This is what we call event time. And then there's something we call processing time in Flink. This is the time when the event arrives at your system, and you do the actual processing. And why is this important? Think about, as an example to motivate this, think about Star Wars, where we have essentially the time when the episodes were taking place is here the event time, and the time when they were published to the public is processing time here from 77 to 2015. And what happened is that episode 1 got released after episode 5 was released, for example. So what this tells you is that events arrive out of order. And this is happening in the real world as well. If you have a stream of data coming from your mobile applications, you will often see them arrive out of order. And if you now go ahead and try to group those things in windows, if you have processing time windows, you will group parts of the stream together that you actually don't want to have together. So here we have the first burst of events are green, the second burst of events are red. You want to group those together. If you only have processing time semantics, you might group different events together that you don't want. And this is actually what we were doing before also in the batch architecture. The files were created when the events arrived at the system, and we chose to ignore that they might arrive out of order, essentially. With proper support for event time, we can get a hold of this and actually group the events as we want them. And again, this is also possible in Flink right now. So what we have here is we say we want to operate on event time, and then the windowing semantics here just change. You have to provide the system a way to extract the timestamps from your records and tell it how far the time has passed within your streams. But this is also actually quite simple, but I'm not showing it here today. So the benefits of handling time in this way are very interesting because we have way more expressive power how we do this. It's very easy inside of your program. You get accurate results for out-of-order data, and the results are actually deterministic. It does not depend on when the events arrive at your system. And interestingly, this is stuff we usually ignore when we do it in a batch architecture, or where we have to go to great lengths in the user code to really handle this well. And if you have proper support for it, your life will get much easier. So this was the first building block of Flink, which is very important in my opinion. The next one is state and fault tolerance. So looking at stream processing, you will notice that there's like this first generation stream processors which were stateless. So you took events, did something on them, and then transformed them, for example. This in itself is already very interesting and gets you quite far, actually. But everything you do in your operator, for example, if you have a hash map in here, will get lost as soon as failures occur, and you have to worry about it manually, how to get the state back. So the new generation stream processors like Flink, they provide mechanisms for state handling, where you can actually tell the system, this is the state I'm working on, and please make sure that everything gets stored and restored on failures. So what you often hear in this context are like the processing semantics you get from the system. The most important ones are at least once and exactly once. So at least once gives you the guarantee that you see each record at least once. So if a failure occurs, in our counting case, it may happen that you overcount, because you just counted something in your operator, then a failure happens, you replay the stream, and you count something again. Whereas with exactly once, the system guarantees that all state within the system is actually really just accounted for once. The top two are within the system, so in this case, within Flink. But what you also want to have is to actually publish this data in a consistent way to the outside world. And this is when we talk about end-to-end exactly once, where you process your streams from somewhere, do the processing within the stream processor, and then consistently publish this to the outside world. So what you get in Flink right now is exactly once guarantees within the system. So you can also configure this for at least once if you desire so. And for some kinds of setups, we can also guarantee end-to-end exactly once. For example, when you read from Kafka, do your processing, you can publish this in an exactly once way to the outside world, like HDFS. And internally, this works by injecting snapshots into the data flow, and these trigger snapshots of the state to which you can then roll back to if a failure occurs. And doing this in the right way will also have impact on the performance you get out of the system. So what was very interesting is like end of last year, Yahoo decided to benchmark Storm, Spark Streaming, and Flink. And this was a very interesting step for the whole branch of streaming, because it was the first benchmark which was modeled after a real-world application. And you can read about it here. So what they did is they had their ad, essentially a counting job where they counted ad impressions. And they consumed the data from Kafka, did some processing within the systems, and published this data to Redis to be queryable outside of the system. And they focused on, so what you see here is the results they got actually. So on the x-axis you have the throughput, that's here up to 180,000 events per second, and the latency you get, so in seconds. So both Storm and Flink were able to handle these, their benchmark with very low latencies in the order of 1 or 2 seconds at the throughputs here. Whereas with Spark, the latency increased with the throughput of the system. So the more records you were processing per second, the higher the latency got. So for the throughput of the stream here, around 2000K, you ended up with 8 seconds of latency. So this was a very nice starting point with benchmarking the stream processors. What we then did at Data Artisans was to take this benchmark and extend it, because we knew that Flink can handle way higher throughput, and we wanted to see how the system behaves. And also there were some shortcomings in the way the Yahoo team implemented this benchmark. So they actually did not make use of the internal state that Flink provides, what I was talking about before. So we rewrote the Flink job to make use of the internal state abstractions we provide, and we got some quite interesting results. So we were able to scale the Storm job to even higher throughputs, because we had a faster interconnect in the cluster. So this were around 500,000 elements per second. And the Flink job, by making use of the internal state, which, let me go back here, which meant that it didn't have to query for Redis for all operations, was scaling to around 3 million records per second. So this was very nice and all. We looked at what's happening in both cases, and for Storm we noticed that it's CPU bound, and there was not much we could do about it. But for Flink, we saw a bottleneck actually in our setup. So the storage cluster and the processing cluster were connected via a very slow interconnect. And that's why we thought about, OK, what happens if we get rid of the storage layer and move the data generation inside the process? And then we saw the system being able to even scale to higher throughputs. Yeah, and at this point only was it bottlenecked on the CPU. So, yeah. Maybe to summarize this, at this point, you have a lot of use cases which you are handling with your batch systems. It works, but streaming is gaining momentum, and the space is maturing in general. And you should start thinking about whether your use cases are actually better served by stream processors. And if you do this, the choice of framework is actually very crucial, because simple applications like counting become very complex in production. And in my opinion, Flink is a very good fit for this, because it offers a very unique combination of the features we just saw. Yeah, this was one part of the stack. Any questions up to this point? Yes?
Is it
Let me just a second, because we're recording.
Is it possible to input at least once and giving a timestamp of the event time?
I think the mic is not on, is it?
Sorry?
I can just repeat the question. Okay.
Okay. So if you give in exactly once guarantee and also a timestamp of the event, is it possible to filter this out on the timestamp within Flink? So do exactly once within the streaming?
I didn't really get the question.
Okay. You have at least once, and you give the event time. So
yeah.
The event might occur twice, three times, and so on.
Yeah.
And is it possible if you separate, if you count or aggregate on the event time?
Okay.
Your output should be exactly once, right?
Okay. So the question is, if you configure if you can get essentially end-to-end exactly once by running your Flink job with at least once configuration, and the answer is no. So. Yeah, because you cannot make any guarantees of what the state is if a failure occurred. So there's no way to publish this in an exactly once way, even if your outside system has support for transactions or whatever. Okay, more questions? You're in the back. Two more in the back. Robert, can you go there?
The mic's not working. So.
Oh, okay, yeah, sure. Yeah.
How you window your data records by event time.
Yeah.
Which sounds kind of cool, but then if your events arrive out of order, how long do you wait until you spit out a result? Like, okay, imagine I am 1995 and I see I have Star Wars episodes 4, 5, and 6, but do I give a result out now which says there are 3 movies, or do I say, yeah, well, there might still be episode 1 which I don't have yet?
So it's a very good question. So I was talking about out-of-order events before, and the question was, what happens if they are very much out of order and you have very late events arriving? How do you close your window? So if you really want to have the complete window, there's nothing you can do about it. You have to wait until all elements arrive by this mechanism of providing low watermarks. But the nice thing is that you can really trade this off. So you can, I didn't show this here today, but you have very flexible triggering mechanisms in the window API where you can say, OK, this is an event time window, but I want to have early results latest, I don't know, like after 1 minute or 1 second or whatever. So you can combine this. So this is a trade-off you have to do depending on the application you're implementing. So, but if you want to have completeness, there's nothing you can do about it. You have to wait. Okay. Yeah. There was another question.
I really like the idea of stream processing, but what I think is that a lot of traditional or relational systems cannot be captured from the interface directly, or can process the deltas as efficient that should be that's needed for stream processing. So you have to deal with a lot of data which should be extracted as a full load. Then you cannot skip the batch processing part.
I didn't really understand the question. Sorry.
You have a database which cannot deliver the deltas, it's the leads and the updates.
Okay.
You always have to do a full comparison. Then you cannot use that streaming mechanism.
The question was,
How do you cope with that? What's your idea about handling the traditional database input?
okay, the question was how to handle traditional database input. I think there's this concept in databases called data capturing. So where you actually do this, exactly this, like stream the changes happening in the database to other systems. This would be one solution. And this would be one solution. And you might have to rethink your whole setup to actually just, maybe let's skip this part, but.
I'm affiliated with the Dutch National Police. We have a system from the 80s which was daily used for registration. And they have not such a change data capture mechanism or something.
Okay, understand. If you have legacy systems, then this becomes problematic, but maybe this is something we should take offline then and discuss. Yeah. Another question here?
I have a question regarding the comparison Storm regarding Flink.
Yeah.
Are there any things which I can do with Storm which I can't do with Flink? Or where do you see the difference between Storm?
I'm pretty sure that the question was if there are some features in Storm that are not like mirrored in Flink. Is there stuff that I can do in Storm which I cannot do in Flink? I would guess yes, but maybe not in the core parts of the system. So as of for at least the versions that were compared here, it was not possible to, for example, work on event time and have state handled by Storm. But this is very hard also to answer because I'm not too familiar with Storm. So.
Do you see any use cases, enterprise use cases, that you would say, yes, for that use case, Storm, for that use case,
Are there any use cases where Storm is a better fit than Flink? I would say that you can handle most of your Storm use cases you will be able to handle with Flink. But this is a very general question, so we would have to discuss in detail. Yeah.
What other source systems can you integrate with Flink? You've shown Kafka and files. Does it work with other message queues?
The question is if we have support for other sources than Kafka and files. The answer is yes. This is a very alive area of the project where we're adding connectors all the time, essentially. We have support for other message queues. And there's added support for reading from Cassandra and writing to Cassandra. This is a very alive part of the project. So adding connectors is a very big part of it. Yeah, there's another question.
When you move from the batch to streaming, like you said,
Yeah.
part of doing batch and doing files in between is also that you decouple systems. So you can do maintenance on one, or if something breaks on the one end, you just wait a little bit, fix it, and then the files are still there and it's decoupled.
Okay.
If you put it on streaming, what are then the consequences?
So
does your architecture not become a lot more difficult because it has to stay live?
the question is that with the batch setup, you have files decoupling the systems, and what happens if your stream processor goes down? So actually, that's not the responsibility. I think not the responsibility of the stream processor, but of the message queue. For example, Kafka. Kafka is responsible for making the events durable, and then you can restart your stream processor and process like just from a later point in time, earlier point in time, instead of just parsing the latest events. Maybe this is something we can also talk about offline later. Okay, yeah.
Are there any plans to integrate Flink in Ambari?
Are there any plans to integrate Flink with Ambari? I'm not aware of.
It works already. So there is
So,
a
okay.
community supported plugin in
So the answer was it works already, so it's already integrated. So it's a very big project. It's also hard to keep track of all changes happening. Maybe I'll continue with the closing of my talk, and then we can also continue with the questions if we have some more time. So the parts I've skipped were like the libraries. This is also a very vibrant part of the project. A lot of development is happening there. We have libraries on the streaming part for complex event processing, on the batch side for machine learning and graph processing. I want to highlight the CEP part of things. So what you can do is actually, we have a DSL where you can define patterns that you are looking out for. For example, here you're looking for temperature events, and if the temperature is above a certain threshold 2 times in a row, within 10 seconds, you fire an alarm. And so this is a very nice API to define these kind of problems. And looking at upcoming features, the community is working on SQL support for both the batch and stream side, and also dynamic state and creatable state. So for example, SQL could look like this, where you say, okay, give me select from this stream all orders where the units are larger than 3, and you would get a continuously updated result table, essentially. So this is work done in collaboration with the Apache Calcite community. Dynamic scaling, so because you keep your job running all the time, it will happen that the load characteristics change on the input. So for example, you have like spikes or nothing is happening, and then you want to rescale your programs dynamically at runtime. So there's support added for this right now, and also for querying the state inside of Flink. So actually, if you remember the benchmark, the window contents were published to a queryable database. So what we are working on right now is to move this inside of Flink, so you can essentially just query Flink and get rid of a big bottleneck. Yeah, if you got interested in this stuff, I would urge you to read our blogs at the Flink project, and also the Artisans has a very active blog. You can follow the projects on Twitter, and also if you have any questions, subscribe to the mailing lists. And I think we have some time now, some time left for questions. Do we? Do you know?
Yeah.
Yeah. So thank you for your attention. Thank you for your time. And yeah, I would be happy taking further questions if you have some. Also offline, we have also other committers here from the project. For example, Robert here in the front. You can also talk to him. Yeah. Thanks for coming.